Okay, students, we are going to do those questions that are mostly level 3 and level 4 from 2015 to 2019, the ones that were difficult in those years. So I hope you're ready. I can see that some of us are pretty ready for this. So let's get started. We already want to start with the algebra part of things. And we had question 1.3. Okay, I think I now have everyone's full attention. So look at 1.3 of November 2017. It wasn't too difficult, but if you look at what they asked you, so let's say for starters, let's say we have that one, a function of x. Let's solve this one. That wasn't a problem because everyone can say x squared plus 8x plus 16 is greater than 0. Everyone can handle this one. Maybe not everyone. Let's just quickly figure out what the brackets were here. What are those two numbers we multiply to get 16? When we add, we get 8. It is 4 and 4. Thank you. So it's x plus 4 and x plus 4. It's a problem when you have an answer like this. One repeating root. So here your roots will be, these are your roots now. That is x is equal to negative 4. The method that we normally use is that we draw a graph to handle an inequality. We put it on a graph, and at this point, we are noticing that our root is here on negative 4, somewhere there, and then the graph is like this. It's obviously concave up. So that's your y, that's your x, and we are here. This graph is always positive. Can you see that? Except for one time when it is equal to 0. And they're asking us, solve for function of x is greater than 0. So you can see that all the time it's above the x-axis, this graph. So you can say, well, it's actually all the values that I can see, that is x is an element of real numbers, except for that one time when it is actually equal to 0, which is at x is not supposed to be negative 4 of all the real values that you have. So that's a solution right there. Or if you're that person who wants to write it in a format that you understand, you can say, well, this part of the graph is above the x-axis. That is from negative 4 going onwards, right? So you write your answer as x is an element of real numbers and x is smaller than negative 4. And you will realize it's not the only part of the graph that is above the x-axis. Even this part of the graph is also above the x-axis. So you have to start again from here, which means you also have to include x is greater than negative 4. As you can see, as you can see here, it's like everything except negative 4. So this notation was going to work a little bit faster this time around. Okay, sorted with that graph. Just one thing before we go. What would be this value over here for this graph if we were interested? That would be 16 right there. It's a very important thing for the second question, because the second question said, for which values of p will function of x is equal to p have two unequal and negative roots? So unequal roots, yes, but they also have to be negative. So when we have a question like that, there are two ways of handling it. So the graph of function of x is still on the board. While it is still on the board, remember p is a y value. So I'm just going to put a horizontal line, and you tell me how many times that line will be cutting the graph. So if I put a line over here, how many times is that line cutting the graph of function of x? That is twice. It means we have two roots, which is this root over here and that root over there. Can you see that those values will be negative actually? It will be negative a value of x. So we want those values of x. We want those values of p. Can you see that p, however, if I ask you to just randomly give me a value of y at this point, what would you say? Just a random one. 4 will be kind of too small, but it can be. As long as it's smaller than 16, it can be the 1, isn't it? So I thought you were going to say 8 or 7 maybe. So p is equal to 7 will give us two roots that are both negative, as you are noticing. Let me just change my p value just to investigate what's going on. Why don't I put it down here? What do you think the value of y is at this point? Anyone? -1, -5, or whatever it is that you put. How many times is that horizontal line cutting the graph of function of x? It's not cutting at all. So by the way, when I'm saying the graph of function of x, I mean this guy here that we started with. This is the function of x if we try to draw it. It's not cutting. So we have non-real roots. So it means if p is smaller than 0 in this situation, we won't have roots at all. Let me help you to see something else. I'm going to move my line again. Now I'm going to put it right on the x-axis. How many times is that horizontal line cutting the function? Once. So one real root, but it's 1. That's the problem. We don't want that. We only want to have 2 unequal roots, but at least we know where to start. If I just move that line slightly above that point, that turning point, like right there, I am back to cutting it twice. Okay, so now at least now I know that p can be anything between 0 and the values that are, say, over here. Look at this time now. There. I still cut twice. What is my value of p at that point? 16. At p is equal to 16, how many roots do I have, or how many times do I cut? Twice. But if I cut twice, this root over here is negative. That's a good thing. But this root here is not negative. It's 0 itself. I want 2 negative roots. So I cannot take p of 16. It won't work. So I know where to stop now, because if I carry on like that, p of 17, how many times is it cutting? That was a good thing. It's cutting twice, but the problem is the other root is now positive. We want them to be negative. So did you establish which values of p we need here? From 0 up to 16. Yes, those are the answers for p. So the answer should be p as in between. We know that 0 and 16. That's the answer. You need to think right there, to investigate, to look at things and get your 4 marks. You know, you start wondering, okay, it's a lot of thinking to get to 0 and 16. So that's why it's 4 marks. All right, I think you are sorted with that one. Let's quickly figure out what else. Yes, dear. Yes. Algebraically. If you do it algebraically, when we do it using algebra, we have a way of saying 2 equal roots. We know that b squared minus 4ac must be greater than 0. But the problem is they also mentioned negative. And now we no longer have anything to help us with that except the graph. If I solve for b squared minus 4ac is greater than 0, I'll be solving for 2 unequal roots, including the ones that are positive, including up there. So it means I may just get my p to be greater than 0, most probably, if I solve that one. I won't have something that will stop me at 16. You see what I mean? Who asked? Oh, it was you. Right. So we can do it algebraically, but we will notice that we cannot cater for that negative roots part. So that's why we didn't go that way. All right. I think you're fine with that part. Let's quickly do this one now. Right. Simultaneous equations. Not bad at all. What should we do now? 2 equations, solve for x and y. We were so happy we can do simultaneous equations until they did that in 2015. She figured it out. It's a perfect square. So we are talking about 2 perfect squares here that are adding to give us 0. Definitely, we know that if it's a perfect square, it's always greater than or equal to 0. That is what we know. So if we have a perfect square, maybe I should just write that down. Any perfect square is greater than or equal to 0. So what it means is that if we have 2 things that are perfect squares that are adding to give you 0, we don't have any other option than for both of them to be equal to 0. You can try to think of it in any other way, but you will realize that only this can work. Okay, is equal to 0, or in fact, both of them should be equal to 0, not or. Because if one of them is not 0, they won't add up to 0. So it's actually and this one is equal to 0 as well. And then you solve. The easier one to handle is this one, because you can just say x minus 5 and x minus 5. I don't know why I put that step over there, but x is equal to 5 twice, right? Once you figure out your x value, you come here, you know that 3x minus y should be equal to 0 twice, and then your x is going to be 5 over here, and then you get your y. What will be your y value, people? 15. Sorted. So that's how you were supposed to handle this one. As you're noticing, it wasn't very lovely. If you are expecting two good equations that are separate from each other, then you get one as that. So we found it was very funny to do. But here you are, you can do it. Well done. Right? There is a need for us to carry on fast, so I'm going to go to that one. I hope you also worked that one out. So looking at this one, I wonder what it is that you did. It happened in November 2018. There are a lot of ways you could have used to handle that, but I would like to highlight one way which works. Is there anyone who would like to say their method, or should I go for mine? Who got to their final answers? We've got quite a number of students. Wow, perfect. So I believe all these people that are raising up their hands did it this way. We have 3 to the power 9x, which is equal to 64. That's a good piece of information. And then we also have this one to handle. But the thing is, the question is asking us to do this one, which if you look at it, the first thing you may want to do is to let that 3 in, and then see what you can do with that. Notice we have 5 to the power root p. So that root 5 there, we don't really want it to stay. So I am going to change square root of 5, this one, to 5 to the power of a half. And 5 to the power of a half, then raised to the power of root p. Are you seeing what I'm doing? Now, this is the expression we have to solve. But what is it that we were given so that we can solve this one? Well, we were told this information, 3 to the power 9x is equal to 64. I am noticing I'm not interested in 3 to the power 9x. I'm interested in 3 to the power of 3x. So I have to play around with this 9x until it looks exactly the way I want. So 9, we know 9 is actually 3 times 3, so I just choose where to put x here. So I am going to do it this way, like 3 to the power of 3x, and raise it to the power of 3. It will be the same thing. What is 3 times 3x? 9x. Perfect. So it means we are still right. If when we are doing exponents, normally we change that 64 to a prime number, and then it will be, you get it, if you do it with prime, it will be 2 to the power of 6. But you don't want things to the power of 6. You already have to the power of 3 this side. You're going to try and make the exponents the same. So 2 to the power 6 can also be written as 2. 6 can be written as 3 times 2. So that's how you are going to pick up that this one can be written as 4 raised to the power 3. 2 squared is 4, isn't it? Now, they all have the same power now. Is 3 this side and is 3 that side, and if the powers are the same, what do we know about the bases? So in our case, we can say therefore 3 to the power 3x is equal to 4. One good piece of information that I can use over here quickly. Right? Another thing I can do before I go and make my substitutions is to play around with what I have here. 5 to the power p 5 to the power root p is equal to 64. In fact, why should I even bother? Because I can make this right here change to 5 to the power root p instead. So look at what I'm going to do in a few minutes. Look at this. I am going to look at the numerator. I'm going to split that one. I'm going to say 3 to the power of 3x multiplied by 3 to the power of negative 3. It's true, right? Now, what I want to do is to actually interchange these two. You know that if I want, I'm talking about interchanging those two powers. So I want us to, I want you to notice that when you multiply this, it will be 5 to the power of half of root p, like this. I don't know if you can see the two. That's what we do when we do exponents. So what I want to actually do is to change that to 5, put root p inside, and then put half. I haven't changed anything. It's still the same expression. If I want to simplify this, it will still end up like this one. It will be raised to the power half of root p. So if I have this, now I can now make my substitutions. With this information that I have now, I can make my substitutions. What did we say was 3 to the power 3x? What is it equal to? 4. And then multiply 3 to the power negative 3. What is it equal to? 1 over 27. Thank you. 5 to the power, this thing inside the bracket. What is it equal to? 64. So we have 64 raised to the power of a half. It's more like square root of 64, really. We don't struggle with stuff like that. Did they say without using of okay, well, they say it. They say it, so I was about to say, put that one in the calculator. So the numerator is 4 over 27. And now we are going to divide. Square root of 64 is well known to be 8. I believe they won't think that we are cheating there when we put multiplied by 1 over 8. So, well, to simplify this, since the calculator is not needed, I'm going to do this. 1 times 1 will be 1. 27 times 2 will be 54. That must be the solution for that one. So, okay, so let's quickly figure out what we can do with the next things. We also want to talk about the sequences and series part of these things. So we want to do the sequences and series. So if you look at this one, it was asked recently in 2019. They give you patterns now which are not easy to pick up. It's not all, they are not compelled to giving you an arithmetic, a geometric, or a quadratic. They can do whatever it is that they feel like, as long as there is a pattern you can notice. That is what happened here. So if you remember your sigma notation, this one you are not going to struggle with, because you will notice that for the first one, this one, you know that you have to sum all terms you get by using this formula, y minus 2, from y is equal to 3. That would be your first term there. So to get your first term on the first one, you put 3 in place of y. So what could you get? What is 3 minus 2? 1. That's the first term. You still have to add. So from y is equal to 3, you go to y is equal to 4. So if you put 4 in place of y, 1 over 4 minus 2, what are you getting? 1 over 2. Let's carry on, put 5. It's 1 over 3. Carrying on, put 6. 1 over. Right. So that right there is the first. I'm not going to do everything. Let's put it in this bracket until we get to 10. Since you're getting tired of substituting, we have to stop at 10. What is 10 minus 2 then? Yes, so the last term is 1 over 8 on this one. Let's see if we are adding or subtracting in between. Actually, we are subtracting. So you were supposed to subtract the second one. On the second one, you are starting on y is equal to 3 and ending on y is equal to 10. So you were supposed to just make your first 3 terms. That's normally what you do. If you make your first term, you have to put 3 there. 1 over 3 minus 1, that is 1 over 2. The next term you put 4. 1 over 3. The next term you put 5. 1 over 4, all the way to the last term where you put 10. 10 minus 1, that will be a 9, all the way to 1 over 9. The good part about these ones is that you can see that the first bracket contains almost the same terms, so you can easily cancel them. What is half minus a half? Do you see that? This one and that one. This one here and that one. In fact, just before 1 over 9, there will be 1 over 8 there. So this one will cancel that one. In fact, everything in the first bracket is going to be cancelled except for that 1 over 1, which is 1. Okay? Then minus. Is there something left that was not cancelled in the second bracket? That is 1 over 9. So what is 1 minus 1 over 9? 8 over 9. Very simple. the 3 marks with. Simple. It's just that maybe people took a long time to figure out what to do with what is available to them. Not bad at all. Now this one, I don't know how it made it, but let's just do it since it's already here. Let's just say it's a level 3 part of things. I hope you notice this is the shaded area, the shaded part. It's quite blurry, but here it is. That's the shaded part of things. So I think you read it's a steel pavilion comprising of 12 steps. First step, 3 meters. The first 3 of the the first 3 steps are shown in the diagram. 5 meters wide. The width is 5 meters of all of them. I wonder why we even need that 5 meters. And then the 1/3 is the rise. So each one has got a rise of 1/3, and then it has 2/3, which is the tread. You were supposed to find the area here of the shaded sketch, the open side, which is the shaded part. It's supposed to be covered with a metal sheeting, and then therefore you were supposed to find the metal needed to cover both open sides. In other words, you need the area of both sides. To get the area of these sides, let me first of all get the area of one side. Please, it's the side that we want. All you needed to do here was to divide it into the rectangles you can handle. There. So this is your first rectangle to start with. What is its length? 2/3. What is its breadth? 1/3. Okay, that's the first one. What is the length of this one? 2/3. What is its breadth? 2/3. In fact, let's just get that area. Let's get the area of one side. To get the area of one side, I'm going to say the first one is 1/3 times 2/3. That's for the first step on one side of the step. The second one, to get the area of that one, I just have to add everything. I have to say 2/3 multiplied by, is that 2/3 again? Okay, let's go to the next one. This one right here, what is this side? It's still 2/3, and then how long is that side? Now it's 1. So because you have to say 1/3 plus 1/3 plus another 1/3. So if you multiply that one, 2/3 times 1, you get 2/3 as well. You want to see the pattern generally. That's what you want. So here, if you say 1/3, carrying on up to the 12th one, 1/3 times 2/3, what's that? 2/9 plus the next one, 4/9 plus 2/3. Now, 2/3, the 2/3, if I want to say over 9, it will be 6/9. Now you can see the pattern. If I ask you for the next term, what will it be? It will be 8/9, carrying on like that. We are going to go all the way to the last term. Remember, there are 12 steps that we have. So I'm calculating the area of one side. Are they forming a pattern? Which pattern is this? It's an arithmetic sequence. Thank you for noticing. I thought it was geometric. It is not at all. What is the common difference? 2/9 all the time. So you're adding 2/9 all through. So calculating the area is going to be child's play. We want the sum for all 12 steps. So in other words, we want sum of 12, but just don't forget it will be one side. So since it's arithmetic, can I just quickly go and put it into this formula? It's 2a, right? Plus n minus 1d. So let's quickly figure out if we can calculate the sum of these 12 steps. The a was 2/9, and it's 12, so it's 11 here. Oh, a was 2/9, right? Oh, yes. And d is also 2/9. Interesting. Those that are fast on their calculators, what are you getting? It is 52/3. So please, people, this right here is the area of one side. But do we have one side of the steps here? We're covering both sides, can you see? So if you want the area of the metal needed, you have to multiply that by 2. So for both sides, you have to say 2 times 52 over 3. And what is that answer? 104 over 3. How many, what is this to 2 decimal places? 34.67 square meters. So did we answer the question? It's always good to check. Calculate the area in square meters. Yes, we did. 34.67. That's what you need. Okay? Not bad. Yes, dear. It's fine. Your terms were multiplied by 2. It's a skill to actually have as well. If you were to multiply these terms like 2 times, so it means the first one was 4 over 9, right? It's like 2 times. The sum will just be double what we had. So you can either multiply at the beginning or you can multiply at the end. We're going to use that skill in no time at all. So I hope you keep that in mind. So let's go and see if there is still something on this one. Actually, there is. And just as I am finishing to tell you that you can use the skill, here it is. This is the time when you need the skill we just identified. If the terms are multiplied by 2, even the sum eventually will be multiplied by 2. I don't think you heard me. So let's just say, take the calculators, and let's say 1 plus 2 plus 3 plus 4. What is the answer to this? It is 10. I'm going to double. Notice this is sum of 1, 2, 3, 4 terms. It's sum of 4 terms, right? Now, if I double each one of the terms, 2 plus 4 plus 6 plus 4, what is the answer? Excuse me, that is plus 8. What answer are you getting? That is 20. Do you see what happened to the sum? The sum doubled as well. We doubled each term, but even the sum here, it's more like 2 times the first one. Because these terms here were 2 times the first term, 2 times tn. These ones we were multiplying by 2, and this answer that we're getting is more like 2 times 10, which is 2 times the first S4. Why am I telling you this? It's because we have that sum up there that we are going to do just now. So look at what's happening. We have an expression that says 3, 2, 1 minus k is equal to p, and something happened. You can see something is happening. The tn is being multiplied by something here. So just make sure the tn looks almost the same. So for us to get to what we want, I'm going to change that one to 3. And then instead of seeing it like this, I'll write it as 2 to the power 1 and 2 to the power of negative k. Okay, from k is equal to 1 to k is equal to 20. I want us to see what's happening properly. If this formula can be the same in some way, we will be able to see what's going on. Notice this right here is the same as saying k is equal to 1 to k is equal to 20. What is 3 times 2, this part? 6. So it's 6, 2 to the power of negative k. And this right here is the one that is equal to p. Now, why am I saying this? Now we have another expression that is almost the same as what we have, 2 to the power minus k, from k is equal to 1 to k is equal to 20. The terms that we have over here, we were calculating terms by saying 6 multiplied by 2 to the power of negative k. Now we are getting them by saying 24 multiplied by that. How are we multiplying? What is the factor here? So 24 can be multiplied, can be said it's 4 multiplied by, so let me put the 4 multiplied by that one over here. So it's more like 4, 6 into 2 to the power minus k. So each term was multiplied by 4 of the second one. Is that clear to you? So what happens to the sum? It's also multiplied by 4. Yes. So since this one, each term, because this is the general term part, This is how we get our Tn. We can see Tn was multiplied by 4 for the second one, because this one it was 6, here it's 4 times 6. So in this situation, this one must be 4 times what the answer for this was p, this one right here must be 4p. That's the faster way of seeing it. You must just know that that's how it works. Okay, should we try a different explanation for that? Or you are sorted? Okay, well, you do understand. Let's carry on. Yes. Okay, so now that we discussed many other methods that you have, can we carry on now? Well, here we have the 2015 paper. Are we together on that? We just have to make sure everyone is here. Right. So this was November 2015. Actually, we can say this one was it was actually more like a level 2 sum, but let's see what's what. So you were supposed to write down the numerical value of an expression for Q6. You were supposed to notice what's happening first. So everything has got that -6, wherever it came from, we are not very sure. And then for the first one, you're adding -3. And then the next thing, you add +5 to that sum and carrying on like that. So it may be a bit tricky to figure out the pattern that we have, but the one thing that makes things interesting is that these terms, the last terms that we are adding, are actually forming some form of a sequence that we can relate to. Can you see that? The last terms. So there are two ways of handling this. Let's talk about this way of seeing the last terms. You are noticing that if we look at -3, which was added for the second term, and then that +5, and then that 13, and that 21, in fact, I shouldn't put that plus. What would be, is there something that you're noticing about those? We are adding 8 all the time, isn't it? So there is a common difference of 8. So it is a pattern. What will be the next term here? 29. So if I want Q6, please people, it means I'll have to go -6, -3, +5, +13, +21, and then say +29. That is how I was going to get it. So I have to think of what it is that I did to get to that Q6. If you're looking, I added the terms of that pattern. Do you see that? So it's like, to get Q6, I said -6, since it wasn't part of the sequence, plus the sum of how many terms? 1, 2, 3, 4, 5. Sum of 5 terms of the linear pattern, isn't it? That's what I did. That's the first method I want you to see. So that's how I got that Q6. Can I have the answer for it? I mean, just so we can answer this one, the first 2 marks. What is that answer? If you add these ones here, what are you getting as your final answer? Are you really going to start adding that now? I thought, hurry up, please, hurry up. That's a numerical expression. It means they want a value there. Oh, like the numerical. Oh, we can also put this, but let's put a value. Oh, you are saying that this is good enough, right? I think I should take that as well and say it's good enough. This -6, -3, +5, +3, +13, and all that. That must be good enough since it's a numerical expression. Okay, what is the value anyway for me? For me to feed my whatever? What is the answer? 59. It means the answer was going to be 59 after, it means after, no, not here. So it was going to be 59. So that was another way of handling things. If you use this way of handling things, if you want to now find the second term, let's say Q, the one that was asked on 3.42 now, you want Q129. you're going to use the very same strategy that we used here. The negative 6 is everywhere, plus the sum of, here we were finding Q6, we added 5 terms. So here it will be sum of 128 terms, like this. So you can, if you sum 128 of this sequence and add negative 6, you will get Q129. So there will be many ways of handling this. I'll take the other one. I'm sure I'm hearing ma'am, what about this one? It works with another method, which you will notice now. Let's do it this way. I wanted you to pick up that it could have been, you could do it this way. That's what I wanted you to see first. Now, sum of 128 terms, it's an arithmetic, is it not? So if we want 128, I'm going to just substitute into the formula. 2a, what was the first term of that sequence? It was negative 3. And the common difference? 8. 2a plus n minus 1, which is 127, and the common difference is 8. So if you do this on the calculator to get S128, you will get something. Do we have the value for this? 64640. That's what I heard. So if you now want Q129, you're going to say negative 6 plus 64 plus this one. What will Q129 become? 643. That's an interesting 64, like this. So nobody wants to say 64,000 at all. Okay, so well, that's the answer that we're getting. That's Q129. That was, according to me, the interesting way to get it. The different way of getting it. If you did it the quadratic way, well, that was too general, isn't it? But you were going to get there anyway. How many of us did it the quadratic way? Oh, we have quite a number of hands. It means you didn't want to think anything different to what you already know. So let's quickly figure out what we could have done with this one. I'm going to erase this method and do the quadratic one as fast as we can. If you do the terms themselves in this one, it means the first term is negative 6. What about the second? Do it as fast as you can. Negative 9. Next. Negative 4, is that what you said? Next. 9. Next. 30. 1, 2, 3, 4, 5. So these were the ones that you were given. If you look for the first difference, what were you getting? Negative. And here. Next. Next. And the second differences were, of course, 8, 8, and 8. Well, then this becomes just a quadratic. It's a mere quadratic number pattern. So there was nothing interesting about this one. So if you wanted, were you going to be able to get the numerical? This was going to be a problem. Huh? Were you going to get it now? You didn't get, if you go this way, getting Q6 was going to be rather, you were going to get the answer for Q6, which was, what was it? No. 50 something, 59. You could get 59, but most probably you were just going to see after, what do you have to add to this one to get to 59, isn't it? I think you were going to get it anyway, one way or the other. You know, a person has to fight until they get to the solution. So at this point, getting Q129, it's not getting TN here. It doesn't qualify for this lesson, but let's just do it anyway. If we want to get TN, we say 2a is equal to 8, and our a is going to be equal to 4. And then we say 3a plus b is equal to negative 3, and 3 by 4 plus b is equal to negative 3. What is the b value quickly? You are not moving at the right speed at all. What is the b value on that one? Negative 15. So your a is 4, your b is negative 15. What is the c value? 5. So after you get your Tn of 4n squared minus 15n plus 5, then getting T1, Q129 is the same as T129 in our case. So if you get Q129, you're going to have to substitute 129 here and get to what you want. Why is it so hot today? What is the answer? 6,4. You're still saying 6,4, right? Okay, good. So that was that one. Not bad at all. Let's go to this one. That was November 2015. Life was not that difficult back then. No, we don't believe in that. We have many ways of getting to the other question. So we are already there. See, it's a sign. All right. So please, people, let's answer this one. So we have a convergent sequence. Which year was this one? Did you pick up the year? It is a 2017 paper. The only trick on this question was that we had what appeared to be sum to infinity on this one, and yet it wasn't. It was starting on 3. And then you start wondering, it's sum of what? You know, if I say calculate the number of terms there, you'll be like in top minus bottom plus 1, but the top has got infinity on it, isn't it? So it feels like it's sum to infinity with the 2 terms missing. So you were supposed to pick that one up. That was the only thing that was there. So truly, if I were to add from T3, according to this expression, can you see I'm starting from 3? So if I add all the way T3 plus T4 going on until if ever there was something we were going to call T infinity, if we were going to add this, we're going to get 1/4. That is what we are saying. So sum to infinity itself is not 1/4, because sum to infinity has to start on T1, isn't it? So if I want sum to infinity in any way, I'll have to include T1 and T2. So T1 and T2 for us, we were told the value over there. T1 and T2 is equal to 2. So we're going to say sum to infinity is 2 plus the sum over there, which we said was equal to 1/4. Are we happy with that? So what is the correct sum to infinity this time that we must keep in our heads? Is there anyone who knows 2 plus 1/4 in here? 5, okay. That's 5 over. Did you say 5 over? No, oh, that's the thing. 9, 5. We just never know what you're saying exactly. Well, that was the correct sum to infinity, but just to make sure things are clear here. Now, once you figure out the correct sum to infinity, you are going to be ready to answer this question, and things will be easy from then on. So why don't we answer it together? So the first question asked, that is 3.1, it asked for us to write down an expression for A in terms of R. T1 plus T2 is equal to 2. It's a geometric, people. What do you do? What does T1? T1 is A and T2 is A times R. So if it's a geometric, you express things in terms of A and R very easily. Using Tn is equal to A, R, n minus 1, like that. Okay, we want to calculate an expression for A. It means I have to take A out, something of this sort, meaning A is going to be 2 over 1 plus. That was enough for 2 marks, more than enough. Now, after you get this expression in 3.1, to get 3.2, you were supposed to now calculate the values themselves of A and R. So to calculate the values of A and R, you may have to now use both this thing that we just figured out and that. So sum to infinity, who remembers the formula for sum to infinity in this heat? A over 1 minus R is equal to 9 over 4. So find an expression that works for you. So I was going to call it equation 1, but why don't I just say 9 multiplied by 1 minus R is equal to 4A. do you still remember that we figured out that a was equal to this? Let me call it our equation number 1. So I am going to say 9. So let's move from here to there. 9, 1 minus r is equal to 4. In place of a, I am going to put 2 over 1 plus r. I can do a lot of things, but I just want to do one thing. Let's just cross multiply. 9, 1 minus r. If I cross multiply, do you see the 1 plus r will come this side? Are we together? Okay, so what is 4 times 2? Sorted there. And the good part is that this thing here is a difference of 2 squares. So you just go and you square these ones. That's what you do to get the answer. So you have 9 here multiplied by 1 minus r squared is equal to 8. Something doesn't. Okay, 9 times 1, that's 9. 9 times that, is that 9 r squared. Are we still working together here? I'm going to take this one to the other side and see what we get. What is 9 minus 8? 1. And then, therefore, r squared. Therefore, if I work here, I'll get r squared is equal to 1 over 9. What is our r? Plus or minus 1/3. But we were going to say plus or minus. However, the question said something, so we can pick what's supposed to happen here. Look, it consists of only positive terms. If your common ratio becomes negative, when you multiply with it at times, it will make some things negative as well as you do that. So we are going to pick only the r that is positive here. So our r is going to be positive 1/3 only. That's the answer we're going to take. After we get that one, we're going to substitute into this formula and say a is equal to 2 over 1 plus 1/3. I believe our a will become 3 over 2. That will be the solution for that one. Okay, I decided to just throw this one in, so I want you to try this in November. The paper 2 one, let's just quickly figure out what that one is before we go to the next page. So definitely you got this one right, and I think you found it interesting, he said. So definitely you were supposed to find your first 3 terms, but here we are going to make a little exceptions. We're going to also put the last 3 terms. So you're starting on a is 38 here, so it means this is going to be equal to cos squared 38 plus cos squared 39 plus cos squared 40. I'm just going to stop here for a while, and then give me the last 3 terms. Less noise in class. There are people making noise. So it is cos squared. So let's start from 50 plus cos squared. 51 plus cos squared. 52. Those are the last 3 terms. Well, if we have those last 3 terms, what were we supposed to figure out about these ones? Who can pick it up? Yes. Yes, we were going to change cos squared 38. Look at this one. We were going to use this identity. We know that sine squared a plus cos squared a is equal to 1. That is what we were going to use on this one. So the core ratios work here. Cos squared 38, it is equal to sine squared. What is 90 minus 38? 52. That's exactly equal. And then this one will be equal to sine squared. What is 90 minus 39? 51. I hope you're seeing what's happening. And this is sine squared 50. Okay. And we leave these ones as they are, the last terms. This one is still cos squared 50, this one is still cos squared 51, and this one is still cos squared 52. There is a trick to this though. We have to know it's 52. I hope you can see that last term. we have to know the number of terms that we have here for us to see what's going on. Notice the number of terms here is top, which is 52, minus 38, and then we add 1. How many terms do we have? I can't hear you. 15. Okay, we have 15 terms. Now, with our 15 terms, it's an odd number. It means one of them, I want you to look at what's happening. This term and the last term will give you 1. That's the first one. So it's 15 terms. It means 14 of them will do what we are doing right now. The next one, that one and that one, will give us another 1. Let's carry on. This one right here and that one right there will give us another 1. We say that we have 15 terms. 2 of the terms are giving us 1. Can you see? So it means we will do that for 14 terms. So we'll have 14 ones on the board, and there will be 1 term left. Which one will that be? The one right in the middle. So in your head, I don't know how you are doing it, but if you go 38, if you write all the numbers 38 to 52, you have to pick up which one is the median or the one in the middle there. Which one will be, if we have 15 terms, which one is right in the middle? The 8th term. So you just have to move from 38 and go 8 units more. So it's 38, 39, carrying on. I'm sure you'll stop at 45. So you will have, like we have indicated, a lot of ones, and we are not going to carry on and write. It's how many of them? 1, 2, 3, 4, 5, 6, 7 ones, right? It's 14, so it means we have how many ones? 7 of them. And then we add cos squared 45, the one that was in the middle. The thing is, you are supposed to know what cos squared 45 is. What is cos squared 45? What is cos 45 for starters? That is 1 over 2. So 14 terms gave us the 7 that we are talking about now. And then we say plus, it was going to be 1 over root 2, but the thing is, I just finished squaring it now. What is 1 over root 2 squared? A half. So 7 plus a half, what are we getting as our solution? (15 over 2). We can leave it as 15 over 2. We did that one without using a calculator. So I thought it was interesting since it had some cosine inside. So that's precisely what you were supposed to do. So copy, if you're copying this, copy it down. In fact, you don't have to copy anything. You understand this. Let's go to the next one. Let's go to the next one and let's see what's what. Now, look at this question 16. It's rather question 3 of November 2016. There was nothing serious, but it is good for dessert for your sequences and series. You were supposed to calculate the value of x. We don't struggle with this now, do we? So we know that a quadratic sequence, what is that one thing that we know about a quadratic sequence? The second difference is, oh, sorry, that's one term. The second difference is the same. So in this situation, let's simplify until we get to the second difference. Apparently x plus 8 is one term over there. The semicolon on this quadratic separates the terms. So x plus, you mean the difference, the first difference. Of course, it's x minus x, x minus minus 1 is x plus 1, and then 3 minus x, and then x plus 5. Then you go for the second difference. Minus x, minus 2x, 3 minus 1, that's 2. X minus minus x, 2x, 5 minus 3, 2. So you got your second difference. What you know is that your second difference is exactly the same. So you're going to equate minus 2x plus 2 to 2x plus 2. Which means if you take this to this side, you get 4x is equal to 0. And your x is equal to that answer. It's not, you won't feel comfortable. You know, after you get x of 0, like in, hello, is it 0 really? But I like what they did. I'm sure they knew that they said if x is equal to 0, it gives you a bit of confidence that maybe I was right. Getting x of 0 is not a good feeling at all. Now, what do you want if x is equal to 0? You want to determine the position of the first term in the quadratic number pattern for which the sum of the first n differences will be greater than 250. It's about understanding what they are talking about. If you get mixed up in those words, then it becomes a problem, really. So what we have to do at this point is let's just substitute 0. The sequence now looks like this. I'm just going to put 3.12 here. The sequence now has negative 1, 0, 3. What is 0 plus 8? They are talking about this sequence right here. What is this now? 0 minus 1, 3 minus 0, 8 minus 3, that's 5. They are talking about the first differences. The first difference, obviously, it forms an arithmetic progression. Let's just finish it off for the love of whoever is looking to see what's going on. So we are really talking about this one. So what is it that we want about the first differences? We want for the sum to be greater than 250. This thing here is an arithmetic, so you want the Sn of that to be greater than 250. Figure out how many terms you need for that sum to be greater than 250. Afterwards, after you figure out the number of terms in an arithmetic one, which is the first difference, then you use that to get the number of terms in the original. I think we did a question like this a few lessons ago. So if this is an arithmetic progression, please people, this is the one we are talking about, 1, 3, 5. Carrying on, it means the next one is 7. What is our common difference here? 2. So we want Sn to be greater than 0. So Sn is already n over 2. Do I really have to remind you the formula? Let's just go and substitute. So we want n over 2. 2 times a, in this situation is 1, right? 2a plus n minus 1d. We don't know what n is, but we know d is equal to 2. We want this to be greater than 250. We want the n value that will make that greater than 250 for starters. Let's go and find it out. Do I have another friend coming to press my board? So at this point, let's simplify it. If I multiply by 2 on the other side, I'll still have n out here. And then I still have 2n minus 2 inside. And then this, it's still greater than 2 times 250 will be 500. So we have 2n squared. Are you still following? In actual fact, we want n squared to be greater than 250. Well, that's what we want for now. We want for n squared to be greater than 250, but what is the n value that will make it equal to 250? 50. What is n? If I wanted to solve, if I had an expression that said n squared is equal to 250, what n was I going to get here? 15.88. 88 or 81? I'm having two answers here. We need one solution. 81. Okay, 81 seemingly winning here. So if n is equal to 15.81, the sum will be exactly 250. So which n will make it greater than 250? Yes. So the next term, it is actually, if I have 16 on the arithmetic, on this second difference, on the first difference, I must have 16 terms. If I have 16 terms, let's go back to the question. Let's remind each other. Determine the position of the first term in the quadratic sequence number pattern for which the sum of the first n terms will be greater than 250. We know that the arithmetic sequence must have 16 terms. That will be the first one that will make it greater than 250 if we sum 16 terms. So if we already have 16 terms on the arithmetic, how many will we have on the quadratic? It's a very easy thing to solve because look on the board right now. How many terms on this sequence that we have here, how many terms can we see that are on the board? There are 3. But on the quadratic, how many are there? 4. For us to have 3 terms on the arithmetic, we need to have 4 on the quadratic. So now that we are saying we have 16 on the arithmetic, it means for the quadratic, there are how many? 17. So we need to have 17 terms on the quadratic so that we can have 16 terms on the arithmetic, and the 16 terms are the ones that will be greater, that will have a sum greater than 250. Am I making sense? I didn't hear if it was a yes or a no. Okay, well, so let's go. It is T17 on this one. Determine the position. So the position will be 17. The 17th position, if you must. All right, so for sequences and series, that was all they could do in 2019. From 2015 to 2019, there was nothing serious about what was going on in algebra and sequences and series. So let's quickly take a quick break here and then carry on and work on the last part, the functions part.